A key to physics is understanding resonance, in our case, both atomic and nuclear. Both classical and quantum physics depend upon resonance to properly identify and explain the unique levels and stability of atomic electron orbitals. Both are able to do so at the atomic level without resorting to relativity. In the early days, neither considered relativity to be needed to understand the nucleus at the fundamental level. But we need to remember that deep electron orbits fall between atomic and nuclear physics. In this region, both the classical and quantum models require relativity. The quantum equations are made relativistic by the introduction of electron mass energy into the expression for total energy. To develop a model of the electron deep orbits, we also need the Heisenberg uncertainty relation and the de Broglie wavelength. To be confined to the nuclear region, the electrons involved must be relativistic. Relativistic quantum mechanics is built upon the Klein-Gordon and Dirac equations. Our starting point is the deep orbit energy levels for hydrogen from relativistic quantum mechanics. Relativity gives the standard levels plus new ones, including those close to the electron mass energy of 511 keV. These values are from the excellent paper by Molly and Vavra in 1993. The relativistic Schrödinger or Klein-Gordon equation is for spin-zero particles, and the Dirac equation is for the spin-1/2 particles. Note that the quantum model of deep orbits has an inverted n order from the atomic orbitals. While atomic levels asymptotically approach zero with increasing n, the deep orbit levels approach the electron rest mass energy. Also, unlike the atomic electron orbitals, these deep levels skip n values. What can we learn with some observations from the quantum mechanical results? The introduction of spin does not cause the deep orbits. The difference in results of the Klein-Gordon and Dirac equations are less than 2 out of 500 keV. That's not a big effect. Deep orbits come from the introduction of the rest mass energy term to form the relativistic equations. The relativistic correction to the Coulomb potential is both from gamma and a term proportional to v squared that strengthens the static potential but weakens the pure dynamic potential. The relativistic correction gives an effective dynamic potential. V effective is not quite the expected relativistic correction, gamma V. There is an interaction term. With gamma equals around 200, V effective gives a potential energy approximately equal to the kinetic energy and both greater than 100 MeV. This satisfies both the virial theorem and the Heisenberg uncertainty relation. Classical physics also provides the atomic and relativistic level. Before getting to the deep orbits, we look at how can classical mechanics treat atomic orbitals. Basically, a classical planetary model of orbits is used, but this is one of bound electron fields and coupled oscillators. The classical model uses emitted or absorbed photon energy, the virial theorem, and the conservation of energy and momentum to determine atomic electron energy levels. Bound electromagnetic fields include electric and magnetic components of the velocity-modified electrostatic field. The non-relativistic electron kinetic energy is equal to the absolute value of the binding energy is equal to 1/2 the potential energy. This comes from the virial theorem. the emitted photon energy, E sub gamma, is equal to h nu is equal to the electron binding or ionization energy. There are less emphasized classical effects. Most representations for the quantum mechanics predicted isotropic electron distribution of the s orbital gives the impression of a circular orbit, but a zero angular momentum state with electron going through the origin every orbit is allowed classically as well as quantum mechanically. The s orbital electrons pass through the nuclear region on an elliptical orbit modified. The near nucleus electron is relativistic. Electrodynamics are involved here. The velocity-dependent electromagnetic field is bound to the electron. It changes with orbital radius. Growth of the bound electromagnetic field increases the electron's effective mass. There is also seldom mentioned classical effects leading to a frequency-dependent model. The dominant bound electromagnetic field frequency is driven by electron orbital frequency. Many sources claim that there is no relationship between the emitted photon frequencies and the electron orbital frequencies, but an electron spends more time at resonant conditions, and photon emission is a statistical process at resonant orbital frequencies. Photon absorption is at a fixed frequency. It drives a resonant electron to higher orbital radius. This lowers potential energy and kinetic energy, since kinetic energy plus photon energy is equal to the potential energy, and it also transfers momentum. Total absorption only occurs if transfer ends near stable state. If the end state is not stable, then the process does not complete and re-radiation or Compton scattering occurs. The low n orbital energy values from the previous plot can be extended down on a log-log scale toward low energy and low frequency at high n values. The n values represent the principal quantum numbers, and the relative frequencies are seen here. But if a relativistic potential is used to bind the electron, the low n electron orbital values can also be extended upward on a log-log scale toward high energy and frequency and cross the photon line again in the 100 MeV range. The electron velocity limit, v less than c, limits electron orbital frequency so that resonant electromagnetic field frequency can catch up. The n values are double valued, but in the Klein-Gordon equation, that's the case. In the Dirac equation, with spin, a new quantum number is introduced. We use gamma here instead of photon because no 100 MeV radiation has been observed to come out of the deep orbits. How does all this help us get cold fusion to work? Electron shape change reflects the effects of relativity. At relativistic velocities, an electron pancakes. Field strength increase as field line densities increase. Orbits precess, their potentials go beyond electrostatics. Effective mass increases with relativistic velocity. Size decreases with relativistic Compton wavelength. we need to consider electrodynamics and magnetics, not electrostatics. Elliptical orbits are an idealism broken by relativity. Now, effective mass, momentum, field, and potentials are all velocity dependent. We can see the effect of relativistic shape change on orbit. Onset of orbit change is more abrupt with relativity as the electron passes by the nucleus. But deep orbit electrons are relativistic throughout the orbit. The kinetic energy to potential energy ratio of stable orbits change from 1/2 to 1 for deeper orbits. Kinetic energy and potential energy can greatly exceed binding energy. A new balance must be established between field strength, mass, spin direction, comptance, and de Broglie wavelength. Since the velocity is so close to c, it is effectively constant, but gamma will increase and the orbit will form a rosette. To fully understand this interaction, we might need to introduce general relativity concepts to define cold fusion models. Can quantum mechanics incorporate all of these effects? That's TBD, to be determined. Both classical and quantum physics predict deep orbits. Both depend on relativity to predict such levels. Relativistic strengthening of electromagnetic forces and effective mass lead to strong interactions with and even within nuclei. Atomic s orbitals may be the key to cold fusion. Their electrons experience relativity during each orbit. Can better knowledge of relativity solve remaining problems? We're trying. There are multiple relativistic interactions between a deep orbit electron and its nucleus that need to be better defined. We should look at them from our knowledge of both quantum and classical physics.